I'm assuming BM is not equal to 0, by the way, because I want that to be like here, I should have said that. My bad. Without loss of generality, there has to be some highest power non-zero, right? So I'm assuming that. So what's the base case? The base case would be m equal to n, right? So if m equals to n, then we have beta equals to b0 plus b1 alpha plus da-da-da-da plus bm minus n minus 1, right? Alpha to the n minus 1 plus bm times what? Alpha to the n, right? But what's alpha to the n equal to? Well, it's just equal to the sum k equals 0 to n minus 1 a sub k alpha to the k, right? Which then you can rewrite as the sum k equals 0 to the n minus 1 of like b sub k. There's a minus that I lost. There it is. Brought it back. Minus b sub m a sub k. And I said m, but I should say n here. M equals n, but whatever. M equals n, so no harm, no foul, right? Alpha to the k. So what have I shown? I've shown that it's a linear combination of 1 alpha, alpha squared, all the way out to the highest power, n minus 1. In other words, Pac-Man's happy. So num num. That's the base case in this induction argument, right? So next I assume, assume what?
Assume k is true, and then you have proof k plus 1.
Right.
Or, I guess, m plus 1, n plus 1.
Oh, I did a slightly different induction in the curses. So I did induction rather than, I chose a different path in the notes. The path I chose in the notes is a little bit better. So rather than doing, I've chose, what am I inducting on? M. Yeah, I'm inducting on M. What I inducted on the note in the notes, in the claim, in the induction claim I inducted on the notes was that alpha to the m. Let me just make this comment. Notes. I basically looked at the claim alpha to the m is an element of, well, the span over f of 1 alpha to the n minus 1, which is just another way of saying Pac-Man happy. So that's what I did the induction on, which was much easier because then the again, the induction was for m greater than or equal to n, so the base case is like automatically true from star, and then the induction case is easier to work on. So let's go that path because I think it's going to be easier to understand. Oh, I'm sorry, guys. Let's see. Basically, I'm just saying proof by induction that m greater than n, and the claim. Let's just say claim that. So sorry. Wasting your time. My bad. I mean, we could have continued down the path we were going, but I think I have a mental block in that direction, so let's go. Let's zig instead of zag. All right, so assume inductively. So, of course, m greater than or equal to n. So m equals to n, and we have alpha to the n, which is an element, element of the span 1 alpha, alpha squared, alpha to the n minus 1 over f by star. Now, I don't know if you remember this linear algebra notation or not. If not, really, it's exactly just what I wrote. It's just another notation for what I've already written at Pac-Man. This is like an arbitrary linear combination of these elements, which is called the span of those elements. But all right, so suppose inductively, and you know what? To make life easier and so I stop writing this over and over and over again, let's just call this whole thing right here Pac-Man. Okay. So suppose alpha to the m is an element of Pac-Man for some, I'm sorry, m is fixed here, isn't it? No, n is fixed. M is moving around. It's m is the variable. N is fixed, I should say. So for m greater than n, yeah. N is we're stuck with n. N is the degree of alpha. That's the fixed thing. So we're trying to do induction on m. All right. Then if we look at alpha to the m plus 1, right? That's alpha to the m times alpha, right? But the thing is that this alpha to the m is what? It's the sum over of b. Well, I guess it doesn't have to. Well, yeah, for some of b sub k, alpha to the k equals 0 to n minus 1, right? That's what it means. That's the induction hypothesis, right? And what is that equal to? Well, that's equal to the sum k equals 0 to n minus 1 b sub k alpha to the k plus 1, right? Which we can rewrite as, the sum. Let's see here. I need to make a change in notation, right? I mean, I guess I don't have to, but I will. J equals, if I make this notation, I'm just going to confuse you guys. Let me not do that. Let's just write it out in gory, silly detail. Probably faster to understand. So this is what? This is, b sub 0 alpha plus b sub 1 alpha squared plus plus b sub n minus 1 b sub n minus 2 alpha to the n minus 1 plus b sub n minus 1 alpha to the n, right? And so we're all good here except for the last term. See that? Like this right here is a troublemaker. But what can we do with that? So what I erased and what I'm now writing are essentially the same calculation, guys, by the way. So it's very silly. I forgot. Come on, there's supposed to be a minus here. So this is minus b sub n minus 1 sum. Let's say k equals 0 to n minus 1 of what? A sub k, alpha to the k. And then grouping like terms, right? So grouping like terms, we have, like b0 minus bn minus 1 a0. Oh, I'm sorry. No. Good grief. Try this again. So this one, gives us a minus b n minus 1 a sub 0. That is the term with no alphas. And then plus the next one is actually b0 minus bn minus 1 times a1 alpha. Eventually you get to b n minus 2 minus bn minus 1 a sub n minus 1 alpha to the n minus 1. So I'm just collecting like terms, and now that's an element of the span, which then proves the induction step. So this is an element of Pac-Man. Therefore, at least the spanning claim is true by mathematical induction. All right. The uniqueness, all right. Well, if we had b0 plus b1 alpha plus da 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 plus bn minus 1 alpha to the n minus 1 equals to, let's say, b0 bar plus b1 bar alpha plus da 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 plus bn minus 1 bar alpha to the n minus 1, right? If you had, suppose you had two different sets of coefficients with respect to this one alpha squared da 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 alpha n minus 1 basis. Well, see what you can do with that? You can put it all to one side, right? Just move everything to one side. What do you got?
Yeah, like b0 minus b0 bar,
Mm-hmm.
b1 minus b1 bar alpha.
Mm-hmm.
That'd give you like bn minus 1 minus bn minus 1 minus times alpha n minus 1.
Right. And what is that? Well, that suggests a polynomial, right? That suggests we can look at g of x, b0 minus b0 bar, plus b1 minus b1 bar x, bn minus 1 minus bn minus 1 bar, x to the n minus 1. And what is that? That is a polynomial, right? Which takes alpha as a 0. What's its degree? Its degree is n minus 1. But p of x was the degree, it was the polynomial of least degree, taking alpha as 0 by definition. Consequently, this cannot be a non-zero polynomial. This must be the 0 polynomial. And the only way that can be the 0 polynomial is if all the coefficients are 0. All the coefficients of that polynomial g being 0 are precisely the conditions that b0 is equal to b0 bar, b1 is equal to b1 bar, and on down the path. So that's the uniqueness. So this is the foundation for everything that remains in these notes, which is that we can build a basis for the extension field using powers, just powers of the adjoined element. Like, so for example, let's see here. So let me get rid of this stupid example. So this one is quite obnoxious. What's the basis? So let's just write down the basis for the examples we have, and then I'll stop going over time.
We just started late. Oh, man. I swear, every time I look down, I'll watch it's like,
We did start late.
it jumps like 30 minutes.
I know. Time flies when you're having fun. What can I tell you? So this one here, right? My alpha is, alpha. Here alpha is the fifth root of 2, right? Is degree 5, right? So the theorem we just proved would say that Q adjoin the fifth root of 2. That's a simple extension. And it is exactly the Q span of 1 alpha, alpha squared, alpha cubed, alpha to the 4th. which is to say that everything in this set has the form like a0 plus like a1 times the fifth root of 2, a2 plus a2 times the fifth root of 2 squared, plus a3 times the fifth root of 2 cubed, plus a4 times the fifth root of 2 to the fourth power, where what? a0, a1, a2, a3, a4 are all rational numbers. So, yeah, this is false. But, however, while this is false, the question is, what should I put there? What should I put there to get that?
To get the square root of 6?
No, to get, what, can you find a single element that a simple extension by that single element actually gives you everything in here? So that's one of the things we'll hopefully figure out next class, by the way. This one up here, I wanted to point out. So the Q adjoin the 2 to the 3 halves we were talking about? Well, 2 to the 3 halves is 2 to the 2 halves times 2 to the 1 half. So it's 2 root 2, right? So this is actually the same as Q adjoin 2 root 2. And it's not hard to prove that that is actually equal to, that in fact is nothing more than this. Q join root 2. See, because, all right, this is irreducible. I'm pretty, I haven't quite proved that, but I think that's true. I got to think of a, well, it's not by Eisenstein. You could do like a reduction, maybe modulo 3 or something. I don't know. What happens if you look at mod 3?
8 becomes, so it'd be x squared.
Oops.
8 becomes 2.
So f bar of x is what do you say? It's x squared minus 2. So we can add 9, right? So plus 1.
Yeah.
So f of x. Plug in 0, what do you get? Plug in 1, what do you get? Plug in 2, what do you get?
1 for 0.
So 4 plus 1, which is 5, which is 2, right? So this is a quadratic, right? This is a quadratic. It has no zeros. Therefore, this polynomial is irreducible over Z3. Consequently, by our theorem, it's likewise irreducible over the rationals. So this is the that's one of our. We have two main tools, Eisenstein and this trick, okay, to prove irreducibility. And it's more pesky when it's higher order than 3, you know. But anyway, my point is that's irreducible. Therefore, this is a degree 2 extension, right? So in fact, that's a degree 2 extension. That means I can write an arbitrary element that as a plus b times 2 to the 3 halves, right? Because that's a plus b alpha. That's all that you have. If it's a degree 2 extension, 1 and alpha serve as the basis, because you go to n minus 1. And the thing is, this is a plus 2b, 2b square root of 2, right? which of course is an element of Q adjoint root 2 for essentially the same reasons. And if you pick for me a plus b root 2, I can rewrite that as a plus b over 2 times 2 root 2, which is a plus b 2 to the 3 halves. By the way, is the element of Q adjoin 2 to the 3 halves. So these two calculations show that Q, what I'm showing in the first line is that Q adjoin 2 to the 3 halves, good grief, I can't write, is a subset of Q adjoin root 2, right? Because I showed an arbitrary element of here is also in there. So that's a subset, right? And then this shows that Q adjoin the square root of 2 is a subset of Q adjoin 2 to the 3 halves. So what do we have then?
Subset, yeah.
Right, so they're equal, right? But there's a theorem you could prove here, right? Theorem, and this is like a useful theorem to know about for calculations. And the theorem is this: if we have F adjoin alpha, that's equal to F adjoin C alpha, where C is an element of F. So like this is not special to the interplay between 2 and root 2. The critical issue here is that 2 was an element of the rational numbers, so we could divide by it to do the trick I did.
Yeah.
And like this would have been a very good homework problem that I should have given you. But as I said, unfortunately, I've already written all your homework, so you're safe. I mean, at worst, it could be on the final. But I'll probably forget. That's like after Thanksgiving break, so, you know.
Where my last question is,
Uh-huh.
so before you told us like the bracket notation,
Yeah,
like there was a difference between bracket and the
that's right.
notation, so what are we at?
So the bracket notation, have I written it anywhere? Brackets here? The only place I did it was, well, of course, in polynomials I try to do it. I did it earlier with this. That was intentional because that's not a field. So that's the smallest, it's actually the smallest ring which contains Q and pi.
So bracket means ring?
Bracket means ring, yeah. Whereas parentheses mean field extension versus ring extension, yeah. Sometimes they're the same. I mean, sometimes they're equal. But anyway, so we will wrap things up next class. And then all we have left is that there's like a remaining blurb from Conrad. So, but, and your test.
Do we just have the exam left? Is there one more test?
There's test 3 and then the exam.
I'm actually happy you're having your test after Thanksgiving because everyone else wants to have their test this week.
Yeah. That's it.
I have presentation for tests.
Well, I don't know, like, in trigonometry, I told them, like, we're going to have a quiz Monday and Wednesday, so make sure you come to class on time. And I had 2 out of 6.